Thank you very much for the opportunity to present my work here. So today I will talk about the final part of my doctoral dissertation that was done under the supervision of Nicolas Andrić from the University of Zagreb. So before starting to formally explain the goal of my research and the results, I will try to intuitively somehow explain first the processes that I'm working with and the goal of my research. So what I'm interested in is a stochastic process that combines two components, a discrete component and a continuous component. And for these kind of processes, I want to discuss stochastic stability. So this means that I have a diffusion process which changes the behavior at random time points. And the switches are controlled by a continuous time Markov chain, which is usually independent of the process, but may depend on the starting position of the process. And this continuous time Markov chain determines the precise time when the switching occurs, as well as the type of the behavior that the process will have after the switch. So the idea to observe this kind of switching processes comes from observing hybrid systems. So these are the systems that, like my process, where we observe some continuous component, and this continuous component changes behavior at some discrete time points. For example, you may be interested in observing the stock price or something, the price of some other object, and then you want to see how the change of the interest rate, for example, may influence the behavior of the process. So this kind of hybrid systems became very popular like some 50 years ago, maybe a bit more, and since then they were extensively researched. So for this type of processes, I would like to discuss the problem of stochastic stability. So what does this really mean? The main problem for me is that the distribution of the process constantly changes. And what I want to see is, as time goes by, will the behavior of the process eventually stabilize in a way that the distribution somehow converges to some fixed distribution. So to get some intuition about this problem, maybe it's nice to see this picture which is quite informal, but on the left side, you see a process where the distribution constantly changes. So somehow it is unstable. And on the right-hand side, we see the process where the distribution is eventually stabilizing and it is converging to some fixed distribution in the limit. So this is basically the problem I want to discuss. Okay, so maybe a motivational example to start. So a very simple case is a case of a Markov chain, a chain lambda, which has two states. So this will be 1 and 2. And let's say that our process starts at point 0, and a Markov chain, the discrete component, starts from state 1. And in the beginning, my process behaves like a general diffusion, for example, with these coefficients. And then my Markov chain waits some random exponential time in state 1. And during this time, my process behaves like a diffusion. When the Markov chain switches to stage 2, the behavior of the process changes also, and now it behaves like a different diffusion with different coefficients. And during the waiting time of a Markov chain in stage 2, my process moves differently. And then lambda changes again to state 1, and again my process behaves like a first diffusion. And then when lambda changes again to stage 2, I move again like a second diffusion. And this happens all the time. So you see how the behavior of the process basically changes all the time. How can we mathematically formulate this problem? So we have a lambda, which will be, lambda denotes my switching mechanism, this continuous time Markov chain. And Pxi is the distribution of my joint process x lambda at time t, which started from point xi. I will explain a little bit later why it is important to look into the joint process, not x alone. So pi is my limiting distribution, or this equilibrium distribution. which we call invariant distribution. And of course, I'm interested in measuring how far away the distribution of my process is from this invariant distribution. In order to measure the difference, I need to have an appropriate distance function. So this will be some appropriate norm. In my work, I discussed two most standard norms, total variation norm and Wattstein distance. And of course, I want to discuss the case when the difference goes to 0 with time. And I want to see if I can find out what is the rate of this convergence. This will be my function R of t. If this works, if this happens, I will call my process ergodic process. Okay, so based on the rate function R of t, I can divide my ergodic processes into sets. First, I have geometrically ergodic processes, which are the processes where the rate of the convergence is exponential. And the second type of processes are subgeometrically ergodic processes, or the processes where the rate is slower than exponential. Okay, now to more formally define what I'm working with. So I'm starting from a stochastic differential equation, which consists of two parts. First part is a drift part, B, and the second part is diffusive part, sigma. So both coefficients B and sigma depend on the position of the process X, as well as on lambda, so on this switching mechanism. So lambda for me is this right continuous Markov chain, and I consider the case when lambda has a finite state space. So S for me will always be a finite set. Okay, so this is the SDE for my process. And the main object that I need needed in my research is the so-called extended generator of the process, which is an operator script L, which consists of two parts. First part, Li, is just the generator of a standard diffusion. So if my switched process consists, for example, of n diffusions, each Li corresponds to the generator of one of those diffusions. And the second part, this matrix Q, will be the infinitesimal generator of the continuous time Markov chain lambda. And it turns out that the generator of this switched process is the sum of those two generators. Okay, and now the first question you might ask is this process that much different than a standard diffusion process, or we can just use all the techniques that we have for a classical diffusion and apply here? And it turns out that even in a very simple case, when S consists only of 2 points, you can construct a switch diffusion where both separate diffusions are, for example, positively recurrent diffusions, but the switched process X is a transient process. And vice versa, you can start from transient diffusions and end up with a positively recurrent diffusion. So this means that it's really not that simple how to see what is going on with X by just knowing what is going on with the separate diffusions which construct X. Okay, just very quickly, I will not go into details, but just two most important things that I will use is the notion of phi irreducibility for a Markov process, which is just a property that says that for a measure phi, if phi of some set A is positive, then the expected time that my process stays in this set A is also positive. And of course, with respect to absolute continuity, you can, if it is an irreducible process, you can find the maximal irreducibility measure psi. And then the process will also be aperiodic if it is psi irreducible, where this psi is now this maximal irreducibility measure, and you can extract from your process some irreducible skeleton chain. Okay, I mentioned that I will consider two distance functions. First of all, distance, total variation distance will be used in a situation when my process is sufficiently regular, namely when it is irreducible and aperiodic. And in the case when this is not happening, when my process is somehow singular, then I will not be able to obtain ergodicity with respect to total variation distance, but in this case, naturally in the literature, one considers the class of Wasserstein distances. For example, this will be the case when our matrix sigma will be a singular matrix. Okay, so the main method that I use is the so-called Lyapunov energy method. And the key idea of this method is to observe LV, so the generator of my process, and this generator somehow describes the dissipation of the energy of my system. So the system will be stable in the case when the energy of the system is somehow stayed inside the system, and when the energy goes out, it dissipates, then the system is unstable. Mathematically, we will capture this stable behavior by observing the so-called this drift condition, this inequality, which says that we have to find one function v such that LV can be bounded from above by minus theta v on the entire space, except on some possibly small set where the behavior can be whatever we want. It can be very bad, but this set C needs to be sufficiently small. So on this small set, the behavior can be bad, but on the entire state space, we need to have this upper bound by minus theta of v, where theta is some non-decreasing, differentiable, and importantly, very concave function. And then if this drift condition is satisfied, then one can conclude that the process is subgeometrically ergodic with a rate r of t equal to theta of capital theta inverse, where capital theta is just the integral of 1 over theta, and theta, of course, comes from this drift condition. So when you find one theta, this function theta will determine the rate of the convergence. Okay, so regarding the existing results, since the theory is relatively new, there are still many open questions, but most of the results obtained before our research were discussing the geometric ergodicity, and subgeometric ergodicity was not discussed for this type of processes. So now I will turn on to the main result. The conditions I will not, of course, all formally explain. I will just try to give the most important ones. So I do need some conditions on my coefficients b and sigma. So I will assume they are locally bounded, and I will assume that the solution does exist, since I'm not interested in the existence of the solution. And furthermore, I will assume that the joint process x lambda is a time homogeneous strong Markov process. So why not x alone? Because the important obstacle in observing this type of processes is that switched diffusion is not a Markov process. So in order to get any results, one needs to observe this joint process x lambda. And I will additionally assume this CB-Feller property, which means just that the semigroup PT maps bounded and continuous functions into bounded and continuous functions. A5 are just the set of some technical assumptions, but important is that I will need this function, additional assumption on my function theta. I will need the derivative of theta to go to 0. And I will assume that the infinitesimal generators of my diffusions are bounded by minus some constant c, theta of v. And here I do not require that all my constants c are positive, but instead I require a6. That is that somehow the weighted sum of coefficients c and the elements of the invariant measure of Markov chain lambda is positive. So this means that some of the diffusions may be bad, may not be ergodic, some of the diffusions will be ergodic, but somehow on average, with respect to the invariant measure lambda, I need to have a nice behavior. Okay, and then the result is the following. So assuming all this that I explained before and the irreducibility and aperiodicity, I obtain I know that my process does have an invariant measure and that it is sub-exponentially ergodic with this rate that I had before. Okay, the special case, how much time I have, just to know?
It's around 5 minutes.
Okay, thank you. So just to go through some special cases to get some intuition about the result. So if theta would be a constant, then my convergence rate would be 1. So this would be sometimes called strong ergodicity in the literature. If, for example, theta is a polynomial, my rate R of t will also be some polynomial. So this will be some condition for subgeometric ergodicity. And the natural case when theta is identity function cannot be covered by my result because I have this condition that derivative has to tend to 0, but this is a case that naturally corresponds to geometric ergodicity, and it has been discussed in some other papers before. So this is a condition for geometric ergodicity. Okay, and as I mentioned, in the case when the process is not regular enough, when we have some singular behavior, we cannot discuss ergodicity or obtain ergodicity with respect to total variation distance. And in this case, we discussed the ergodicity with respect to Wasserstein distance. We need to adopt the notion of Wasserstein distance for this joint process. So I have some distance function rho, which measures the distance between xi and yj, and then I have the Wasserstein distance between two measures mu and nu defined in the standard way as Wasserstein distance is defined, but just with respect to this distance function rho. Okay, and the conditions that or the assumptions that we need to impose in this case. So this case, since it's a bit complicated, I discussed only in the situation when the diffusion matrix rho is a constant, but it may be a singular matrix. So this is we don't have any restrictions in that way. But I assume my Markov chain does not depend on the position x. Okay, I will assume that B satisfies the linear growth condition. So it is mostly linearly growing, and we will have some convex function I. And the most important condition that ensures this ergodic behavior is usually called asymptotic flatness condition in the literature. And it basically says, it basically enables you to control the behavior of your process. So what does this mean? Means that the x minus phi, bxi minus byi can be bounded by some constant ci. And again, these not constants, if they are all sorry, this should be minus ci. If they're all positive, then all diffusions would be ergodic, but we do not need them all to be positive, just somehow on average, these ci's have to be positive. And then with when we have all these conditions, we have some we can conclude that the difference. So somehow we have we have the result that the difference between two distributions will tend to 0. But in a special case when psi appears here in this asymptotic flatness condition, if this psi is, for example, a polynomial, we can also conclude that the rate of the convergence is polynomial. And if psi, for example, is a linear function, that we can conclude that the rate of the convergence is exponential. Okay, and just to finish my talk, I will just give some example which shows that this result is really somehow surprising and interesting. So if you can construct a very simple example where lambda has only two states, 1 and 2, and you start from some two diffusions, B1 and B2, with very simple definition. And then your first diffusion, so when lambda is equal to 1, for this diffusion turns out to be not irreducible and aperiodic. It does have a unique invariant probability measure, but the convergence cannot be exponential and cannot hold in the total variation norm. Also, the second diffusion is not irreducible and aperiodic. In this case, it doesn't even have invariant probability measure at all, but the switch diffusion or the joint process x lambda, which is not irreducible or aperiodic, will be subgeometrically ergodic in Wasserstein distance with a polynomial rate. So starting from two diffusions that are not ergodic, you end up with a switch diffusion with a process that is a sub-exponentially ergodic. So, okay, thank you very much for listening, and I'm open to answer any questions.
Petra is right on time, so we have time for questions. Okay, I don't see anybody. So maybe I have one question. So about limiting measure pi, is it, do you have like an explicit construction of it? Or for example, is it a mixture of the invariant distributions of these components, or probably not, but yeah, that's my question.
So no, basically we do not know how this pi looks like. In general case, it is somehow the mixture of the pi's from general diffusions, but for those starting diffusions, we also, if they're ergodic, we don't know how pi looks. So in the end, we don't know how pi looks. And this is maybe not a good thing about this method, is that the method itself does not give you the formula for pi, but you just know that this invariant distribution does exist. And in some simple cases, it can be constructed, but on general, no, I don't know how it looks like.
Okay, Andre?
Thank you. Again, hopefully others will ask questions. My question relates to the usage of Wasserstein distance between distributions. Would anything change in terms of the properties if any other distributional measure would be used? Thanks.
Yes, so the proof really does depend on the construction of the Wasserstein distance. So the second result really is only working in the case of Wasserstein distance. If there will be some other type of function, then I would not be able. So the proof, I didn't tell anything about the method for the second proof, but we use some coupling. So we construct some coupling, and then we obtain this ergodicity, and we really do use the definition of Wasserstein distance. So I believe it's not working maybe for the general norm.
Okay, thanks.
I think.